Okay, now what we want to do here is start to apply the first law for control volumes. And we're going to take a look at two related type of devices, a nozzle and a diffuser. And I believe these are in your homework a little bit too. So this is handy for your homework. A nozzle is a device designed to increase flow velocity. Everybody should have familiarity with a nozzle, because if you ever used a garden hose, that's a pretty good nozzle, okay? And if you ever sprayed anybody with a hose, you probably used a nozzle, okay? Because when you think nozzle, think of your garden hose and think of the attachment, the sprayer, because what it's trying to do is it's trying to take the pressure from your water line and convert that water at a certain pressure into a much faster flow velocity, right? If you take off the if you take off the end attachment and you look at the velocity of your flow, right, it doesn't shoot out the hose, right? It only shoots out the hose when you add the thing on there, or you use your thumb, I guess, too, right? But you add the handle, the nozzle on there, and that enables you to shoot the water, right? Because that's what a nozzle is. Now, a diffuser is the opposite, basically. It's trying to slow down flow, but really it's doing so to increase the pressure of the flow. Okay, so it's the opposite effect. You've got pressure and you've got velocity. If the pressure goes up, the velocity goes down. If the velocity goes up, the pressure goes down. Okay? There's an equation you're going to learn in fluids called Bernoulli's equation. Very important equation. It relates pressure and velocity of flow. Okay? That's why we can fly in planes. It's because of Bernoulli equation. Okay? That's how flight works. Okay? And it's very important for a lot of different flow situations. So we're not going to get into all that, but realize a nozzle and a diffuser, they're used a lot in aircraft, nozzles and diffusers. Also advanced aircraft, advanced propulsion systems, things like that. Nozzles, diffusers, all the time. Okay, so very important devices. Some typical assumptions we're going to make. We like to simplify, right? Typical assumptions. First of all, we're going to assume that nozzles and diffusers do no work. Okay? They don't really do any thermodynamic work. Okay? That's not the point. Second of all, we're going to assume that the nozzles and diffusers have no heat transfer. Okay? Is it possible somewhere out there there's going to be a problem that has a nozzle or diffuser with heat transfer? Maybe. Okay? But almost all cases we're going to assume it's adiabatic, no heat transfer. Okay? That's another one. Another thing that we're going to generally assume is that the potential energy effects are small. Okay? Potential energy, PE, potential energy effects are small, so we're typically going to ignore the potential energy effect because nozzles usually and diffusers don't change the elevation of the flow, typically. Oh yeah, kinetic is going to be very important. Yeah, kinetic energy is definitely a very important part of a nozzle or diffuser. You can't ignore kinetic energy in a nozzle or a diffuser. Okay? But the potential energy is typically small. Okay? And so those are going to be some important property relationships that we're going to look at when we analyze nozzles and diffusers. Okay? So let's get into an example or two here. So here we go. We got steam at 3 megapascals, 400 degrees Celsius. It enters an adiabatic nozzle steadily with a velocity of 40 meters per second and leaves at 2.5 megapascals and a much faster speed, 300 meters per second. So the nozzle appears to be doing its job. Determine the exit temperature and ratio of inlet to exit area. Okay, so here's how I draw a nozzle. That's a nozzle, okay? Basically, it's just, it looks like it's like a funnel, but you're funneling it to a smaller cross-sectional area. Okay, that's how I draw a nozzle. And going in to the nozzle is steam at 3 megapascals, 400 degrees Celsius. Okay? Got that. And we also know it's going in with a velocity of 40 meters per second. And it's exiting with a velocity of 300 meters per second. And we know that it exits with a pressure, call it P2, of 2.5 megapascals. P1 is 3 megapascals. T1's 400 degrees Celsius. So notice that the pressure drops. The pressure drops, the speed increases. Okay? That's what typically happens. If you have a pressure drop, you increase in speed. That's what a nozzle does. Okay? Now it asks us also to get the ratio of the inlet to the exit area, but notice that the problem does not tell me either one. It does not tell me the inlet area or the exit area, does it? Okay? In fact, I've got to figure out even how do I get that into my equations. Well, we'll get to that when we can. Let's do the first part. It says determine the exit temperature. Okay? Determine the exit temperature. Okay? The one thing I got is the first law of thermodynamics. Okay? And in this class, you know, pretty much from now to the end to the final, if you're ever stuck anywhere, my goodness, write the first law. Okay? And I just gave you in the previous lecture 3 different forms of the first law for control volumes. This is a control volume. Mass is going in, mass is going out. Okay? 3 different ones. Okay? So I guess, I hate to make things more confusing, but you have to kind of say, okay, what's the best form of the first law I can write for this? Okay? Anybody have any ideas or thoughts? I gave you 3 different forms in your previous notes there. It's definitely a CISO or CISO, single input, single output. So we got that. Okay? But I don't have m dot, do I? Do I know the mass flow rate? I don't think so, right? So since I am not given the mass flow rate, I'm going to start with the one that does not even have mass flow rate. I'm going to write this out. I'm just going to write Q minus W is equal to H2 minus H1 plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. That's the first law of thermodynamics without mass flow. And the reason I'm not using the one, I'm using the one without m dot is because I don't have m dot, and so I think maybe that's a good place to start. Now, we got to make some assumptions here. This is going to simplify, right? It's adiabatic, so there's no Q. There's no work either. Good, no W. What else? Potential energy, we're not going to look at that either. Not for nozzles and diffusers. So all of a sudden, I've made a much simpler equation. Okay? In fact, I'll just write 0 equals H2 minus H1 plus V2 squared minus V1 squared over 2. Okay? Now, I can simplify this, or I can actually substitute pretty much everything but H2 into that equation, right? Because I certainly know V1 and V2, that's easy, right? V1 is the inlet velocity. That's 40 meters per second. V2 is the exit velocity. That's 300 meters per second, okay? But I don't think I can get H2. That's the enthalpy at the exit. Why can't I get H2 at the exit in that formula? I don't have temperature, I only know pressure, right? I only know one thing at the exit. So I probably can't get H2, but I can probably get H1, and then once I look at that equation, all I have left is H2, right? So I can get H1. How am I going to get H1? Well, that's not going to be that hard. If you look at it, I know the pressure is 3 megapascals and the temperature is 400 degrees Celsius, and it's steam, so I can pull out my tables. So I'm going to go here. I'm going to pull out my thermo table, and I'm going to go to water, okay, I'm going to go to water at 3 megapascals, 400 degrees C. I'm thinking it's superheated, okay, and it is, all right. Okay, so I found the 3 megapascal table for 400 degrees C, and so I've got my H. Let me highlight it here. There it is. That third column there is the H for 3 megapascals, 400 degrees C. It's 3231.7. Okay, right? 3 megapascals, 400 degrees C, and that is steam, right? Yeah, superheated water, so we're good. 3231.7. So let's go back. Okay, 3231.7 kilojoules per kilogram. Okay, so it looks like if I just substitute everything, I can do it, right? I can just solve this. So let me substitute everything in. Let's see here. 0 equals H2, which I don't know, minus 3231.7 plus V2 squared minus V1 squared divided by 2. I can solve for H2. How would H2 help me get the exit temperature? Remember, I don't really care what H2 is. I want the exit temperature. You can look it up in the tables because now if I have H2 and I already know P2, the exit pressure, now I have two pieces of information. I should be able to look up the exit temperature. But we have to be careful here. I have made a goof with that last equation I wrote. Something is wrong. And it's a mistake a lot of students are going to make unless you're looking out for it. I've goofed somewhere. Anybody spot the goof? It's a goof. It's a little harder to spot. It's nothing to do with H1 necessarily. I mean, I suppose it could, but it's the right number. I mean, it's certainly, there's nothing wrong with the number. I've made a goof. I heard somebody talk about units, and units are the answer. The units here are wrong. I'm adding two different numbers that have the wrong units together. When you add numbers, they all have to have the same units, okay? Well, let's see. The units of this H1 right here is kilojoules per kilogram, right? This is here, this is meters squared per second squared, but if you work it out, by the way, you can convert that. We've done this before, but you probably forgot because it was like week 2. This turns out to be the same equivalent units as joules per kilogram. So I'm adding kilojoules per kilogram to joules per kilogram. Okay, this is a very common mistake when students get to this point in their work. This happens all the time. Students come to my office and they go, "I'm not getting the right answer," and I'll go, "Oh yeah, you didn't convert that." Okay, so the kinetic energy term, you have to make an adjustment here. We have to make an adjustment. Okay, so what we have to do is we have to multiply that kinetic energy because 1 kilojoule is 1,000 joules. So you basically have to divide by 1,000 of that second term there. Okay? That's what you got to do. If you don't do that, you're going to get the wrong answer. So you do that, you work it around. Let's see here. And I believe that when you work this out, you get H2 as 3187.5 kilojoules per kilogram. If you work that out, okay? So how does that help me get T2? Well, here's what I know. Remember, I also know P2 is 2.5 megapascals. So I better go back to my table here. I'm going to go back to my table, and I'm going to try to find out what is the temperature when I have a pressure of 2.5 megapascals and an H of 3187.5. Okay, so I go back to my tables, and I'm going to go to pressure table 2.5 megapascals, and then I'm going to go to the value there of 3187.5. If you go to 3187.5, you'll notice that you're pretty much going to be, okay, between 350 degrees Celsius and 400 degrees Celsius. You see that? 31, you got 3187.5. It's between 3127 and 3240. Okay? Basically, it's almost halfway between them. All right? It's about halfway. If you work it out, it's a little bit more than halfway between 350 and 400. I believe if you work it out, you get the temperature by doing interpolation between those two values and using the fact that you know what the H is here. You work out a temperature of about 377. Okay? It's about halfway. Okay? So you're going to work out a temperature of about 377. I'll just do that. Okay? Pretty close. So that's T2. That's the exit temperature of the nozzle. What about the other part? It asks also for the ratio of the inlet to exit areas. How am I going to get that? Any ideas? But area, area is not in my first law. I can't use the first law to solve for area. It's just not there. So what else do I have? What do I have any formulas that have area in them? Yeah, exactly. I got the mass flow formula, right? Yeah, that's the key. The mass flow, remember this? The mass flow is equal to the density times the velocity times the area. The mass flow, remember this is a single input, single output system. The mass flow in is the same as the mass flow out, right? So what that says is that the density times the velocity times the area going in is equal to the density times the velocity times the area going out. Right? Okay? So I want to solve for the ratio, what is it, A1 over A2. So now I'm going to manipulate this equation here to solve for A1 over A2. Okay? Well, that's not too hard. A1 divided by A2, manipulating that equation below, right, is going to be equal to rho V1 divided rho 1 V1 divided by rho 2 V2. Okay? Now the velocities are easy. The velocities are given in the problem. The velocity 1 is 40 meters per second, right? The velocity 2 is 300 meters per second. The question is, what are those densities? What's the density coming in and what's the density going out? How would I get them? Specific volume, and then I get specific volume on the tables, right? Exactly. So all I have to do here is I have to realize that, okay, I want rho 1. Rho 1 is the same as 1 over specific volume 1, and I could look that one up on the tables. In fact, I go back to tables here. What was it? I think it was 400 degrees Celsius and 3 megapascals, right? So it's 0.09938. So this is 1 divided by 0.09938. Somebody do that real quick on their calculator. What's rho 1? It's basically about a little bit over 10. 10.06, I think it is, something like that. What's 1 divided by 0.09938? It is 10.06. I wasn't sure. I didn't want to give you the wrong information. So that's going to be 10.06 kilograms per meters cubed. So you can put that in for rho 1, 10.06 kilograms per meters cubed. Okay? And then for row 2, you got to look that up. Now, of course, it's a little bit more confusing for row 2. Row 2 is going to be, of course, 1 over the specific volume of 2. The specific volume of state 2, you have to read it off this chart here. It's going to be basically halfway between the specific volume of a temperature 350 and the specific volume of a temperature of 400.
Okay. It's like adding together, divide by 2.
You'd be pretty close, yeah. I mean, it's pretty darn close. If you do halfway, let's see here. Actually, I think I remember this one. It's a little bit more than a halfway, so I'm going to work it. I think if you work it out, I think you get 1153 is the specific volume, 0.1153. So I think we're talking about 1 divided by 0.1153 meters cubed per kilogram. And if you do that, 1 divided by that, you get like 8.68 kilograms per meters cubed. So you get 8.68, okay, there. So then if you work out the whole thing, did I want A1 over A2?
Yeah, I think it's A2 over A1.
The ratio, oh, did I do that backwards? I know something went wrong here. So, oh yeah, I'm sorry. This should have been A2 over, I wrote A2 over A1. I'm sorry. Because I should have done, yeah, this should have been, what I was actually writing there was A2 over A1. Okay, what I actually wrote there was A2 over A1. So A2 over A1 is 0.1546, but the answer is really the reciprocal of that. It's about 6 point, so the actual answer, A1 over A2, is about 6.47. So my mistake on that. I was actually solving for the reciprocal, but you can just figure that out. Okay? Okay. Okay, we're going to go through the next one pretty quick. It's very similar. It's almost the same thing. Okay? It's just, I do have English units on this, so we'll go through it fairly quickly and be able to get to it real quick here. Air at 13 psi and 50 degrees Fahrenheit enters an adiabatic diffuser steadily with a velocity of 600 feet per second and leaves with a low velocity and a pressure of 14.5. The exit area is 4 times the inlet area. You know, here's how I draw a diffuser. It's the opposite of drawing a nozzle. It opens up, okay? So what you have here is you have it coming in at a pressure P1 of 13 psi, and you got a temperature of 50 degrees Fahrenheit, and it's coming in with a velocity of 600 feet per second, okay? It's leaving with a pressure, of P2 of higher, 14.5. You don't know temperature. It says the velocity is low, so it's a low velocity, whatever that means, right? Okay. And it says also, by the way, the exit area is 4 times the inlet area, so 4 times A1 equals A2. Okay? Again, where do we start if we don't know what to do? First law, all right? Do I have a mass flow rate given to me? No, right? Do I see a mass flow rate anywhere? No. So I'm probably going to write the first law without mass flow. I'm going to write Q minus W equals H2 minus H1 plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. Okay? Now obviously, again, I can simplify this, right? I can take out Q, I can take out W, I can take out the potential energy term. Okay. Let me see what I can substitute here. Now this is air. Don't forget this is air. I'm given the temperature and pressure of air. Do you think I can get H1? Yeah, I think I can, right? So I think I can get H1 for air by looking at the tables. Okay? Now, air is given to me as 50 degrees Fahrenheit, but if you go to the tables for air, you've got to have it in absolute. That's the same thing as 510 Rankine. So let's go to our tables and look up H1 for air, 510 Rankine. If we do that, we got to go to English. Got to go to our English tables here. Keep going, keep going. There it is. Okay, now I've got the H for air for 500 Rankine, and I've got the H for air for 520 Rankine, right? But I don't have 510. But no big deal, right? That's a simple interpolation. 119.48 plus 124.27 divide by 2. Oh, you get 121.9. Okay, so the H1 is going to be 121.9. 121.9. And that's BTU per pound mass. Be careful. That's not kilojoules per kilogram, right? We're in English units. So it's BTU per pound mass. Okay. And I know what V1 is, right? V1 is given to me as 600 feet per second. What do you think V2 is if they say it's a low velocity? What do you think that means? I mean, that's kind of weird. It says it's a low velocity. Assume 0, and especially assume 0 because we're squaring the velocity. Notice that we're squaring it. 600 squared is a really big number. If it's low and it's squared, it's probably not a big number. Okay? So we're basically going to assume that the exit velocity is 0. So now we can plug in our numbers here. This is going to be 0 equals H2 minus H1, which is 121.9. This is BTU per pound mass. Okay, plus the final velocity is 0 minus the initial velocity is 600 squared divided by 2. No, but you do have to check units. Remember, the divide by 1,000 thing was because we're in kilojoules per kilogram and meters per second. Now we got even more mess of units. Because what's the units of 600 squared? What is those units of that second term there? Feet squared per second squared. But I've got BTU per pound mass. How am I going to add BTU per pound mass to feet squared per second squared? Okay, this is where you desperately jump to the back of your book and you go, give me something back of my book. And it delivers for us. Because if you go to the back of your book, it will actually tell you that 1 BTU per pound mass is equal to 25,037 feet squared per second squared. 25,037 feet squared per second squared. I don't know. I didn't know that. I mean, it's not something I memorized. But I know I can jump to the back of the book and get that. So what you can do here practically is that you can take this whole thing here and divide by 25,037, and you will get it in BTU per pound mass. Okay? Because you're taking something feet squared per second squared, you've got to divide that by 25,037 to get BTU per pound mass. Okay? So if you work that out, you get H2. You got to bring this, both those terms are negative, by the way. Minus 121.9. The second term is going to be minus 600 squared divided by 2, and then divided by 25,037. So if you work this out, 600 squared, it's a pretty big number, right? Divided by 2. Divided by 2537. Okay, then it doesn't become so big. If you work this out, you get an H2 of 129.1 BTU per pound mass. So if you have that as your H2, how do you figure out your exit temperature? What else do you know about the exit? Do you know anything else about the exit? Pressure. Pressure is 14.5 psi, right? So if I'm giving an H2 of that pressure, well, hold on a second. If I just go to my tables, right, for air, remember this is air. If I go to my tables, look at this. I have an H. If I have 540 Rankine, my H is 129.06. That's pretty darn close to 129.1, right? So I'm going to go with that. I'm just going to basically say the tables tell me that if I have an H of 129.1, I've got a temperature of 540 Rankine. So this basically says, okay, T2 is 540 Rankine, which, by the way, is what temperature in Fahrenheit? Well, T1 was 510, so it only went up 30 Rankine. So it went from 50 to 80 degrees Fahrenheit. So the temperature went up to 80 degrees Fahrenheit. Okay, now, lastly, real quick, we're not going to do this. How do you get the exit velocity? Which is weird because we just said the exit velocity was 0. Now it's asking me to solve for the exit velocity. Any ideas? You can't, because in this one you assumed it was 0 to solve it. So you're going to have to use something else. You're going to have to use this. You're going to have to use that. Remember, it gave you the exit area is 4 times the inlet area, right? It gave you the fact that 4A1 equals A2, and since you can say this, rho 1 V1 A1 equals rho 2 V2 A2. And you know this relationship, you can work it out and solve for the actual V2. You'll find it's fairly small. Okay, so you'll get a pretty good assumption. That's all you have to do. It's not worth our time to do it again, but that's what it is. So, you can't. You have to solve this for A1 over A2, and then plug in. So here's what you have to do. Let me just real quick. You have to do is you have to say, I have to divide both sides by A1 and get the ratio, because you know that, for instance, A2 over A1 is equal to 4, right? So that's what you have to do. You have to divide out. Okay, that's all. It's not worth doing too much.